Yes, hello. Welcome to the webinar that we're talking about today, titled Modeling Fluid Flow in the Power Generation Industry, Challenges and Solutions. For those of you who don't know me, my name is Trey Walters. I am the original founder of AFT. My current title is chairman and founder. I was the president of the company for 30 years. And in the last couple of years, I've been able to step down from that by my own choice. But I'm still active with AFT, teaching training classes, doing development, etc., and doing webinars today. So let me make sure everything is looking good on the webinar here for audio and everything. So I guess if there's a problem, yeah, go ahead and put something into the chat. And with that, we will get going. One of my favorite movies is the movie Apollo 13, based on a true story, back from in 1970, about the accident that happened on the Apollo 13 moon mission. And there is a scene that happens in the movie after the accident, and the engineers in Houston are trying to figure out what what are their parameters and what are they going to do, and how are they going to get the astronauts safe back to Earth safely. So one of the engineers playing a character named John Aaron, he makes this statement: "Power is everything." And that's really true for the Apollo 13 mission, and it's really true as well today for our everything that makes all of our modern society go. Without power, nothing happens. And so this is a critical infrastructure, and it's continuing to evolve. It has challenges, and there are some solutions, and we'll talk about some of those here today. So this is the agenda of what I would like to talk about. I'm going to start off just talking real quickly about our products and some of the key features that we have that are make our software so useful for the power industry. And then what I'm going to dive into are some case studies and technical publications that we've done around our four main products: Fathom, Aero, Impulse, and Extreme, in power industry applications. And then from there, we'll draw some conclusions. And then there are some resources and links, and there should be a document associated with with the webinar that you can download that has a PDF that has hyperlinks to all the documents that I'm going to refer to here in the resources and links. Okay, our software products. So some of you might not be users at all. Some of you might use one, some might use all. I'll just real quickly summarize what our software products are, and then we'll dive in a little more deeply on how they get applied in the power industry. So our most well-known software is AFT Fathom. I wrote Fathom 1.0 and 2.0 all by myself way back when AFT was getting started, still in the basement of my home at the time. It is a tool for incompressible pipe flow analysis and pipe networks. 30 years ago, so that came out in 1994. In 1995, I wrote Aero 1.0 and worked on that heavily in the years after, which is AFT Aero does compressible pipe flow analysis. And a lot of people will tell you, me included, but a lot of people out in industry will tell you that it's far and away the best and most accurate tool for simulating compressible flow, and especially some of the hard things like heat transfer, real gas analysis, sonic choking. And we're going to look at some examples, an example today around that. In 1996, and over 29 years ago, I wrote about 99% of the version 1 of AFT Impulse, which does surge, also known as water hammer in the English language, also does pulsation analysis. And then 4 years ago, we released our fourth software product, AFT Extreme. Extreme does steam and gas transient analysis, but high-speed transients that are driven by at acoustic speeds. And so, and it definitely has many applications in the power industry as well. Okay, so here's some key features for the power industry. So there are certainly other software products that do analyses that cross over into the power industry, but there's some things that we do that really goes beyond what a lot of typical pipe flow products do. For example, we do a coupled heat transfer modeling and a system thermal balance, thermal energy balance on the entire system. And that's coupled together with all of the flow and pressure drop modeling. Both Fathom and Aero do the heat transfer modeling. Aero has done it from version 1 30 years ago. Fathom, I think we added it in version 3, which would have been about 28 years ago. So we've been doing this for a really long time. I'll show you some examples. One in particular that makes heavy use of this in an application. So it's not just the flow modeling, but the thermal modeling was critical on one of these customer applications. Another thing that we do, and we've been doing this for over 20 years, is we have an add-on module for Fathom and Aero called the GSC module, Goal Seek and Control. It's multivariable goal seek and control. And as far as I'm aware, we're the only company that really offers that as multivariable goal seeking. This is something that's been available for 20 years, maybe 20, 24 years in our software. And I'm gonna, let me see, I'm not sure if this gets used in one of our examples today, but we'll talk about it where it does pop up in the resources. Another a significant issue in the power industry is a surge transients, a water hammer, or steam hammer, or gas hammer. And our AFD Impulse and Extreme software are designed to help simulate those types of applications. Both Fathom and Aero have add-on modules for bulk transient simulation, slower transients. We call those XTS modules. Something that we're really good at, I think we're probably the best software in the market, is and the most accurate, and I'll talk a little about why as we get later towards the end of the presentation, is predicting what the imbalanced transient forces are on piping that occurs during a liquid or a gas or steam transient. So we'll talk about that. Something that we've had in our software for like 25 years now is a scenario manager. Excuse me. And a couple of the applications today that we'll talk about made extensive use of our scenario manager in trying to handle all the different operational situations. And so those of you who aren't familiar with our software, having used Scenario Manager, it's a tool that keeps all of your different operational cases in a single model file. So you don't have multiple model files to model out the 100 different cases that you're looking at. It's all kept in one, and they're all linked together in a logical way. Our software also has many features to help with different types of code compliance, whether it's ASME and FPA, things like that. And so those are built into our software, and our software helps in those areas. Okay, so let's talk a little bit here about what applications other companies have used our software for. Okay, so power industry, and so I'm going to talk first about power generation, and then I have another slide after this. We'll talk a little bit about other types of power generation and energy storage where our software gets used. But over here on the left are a whole number of power generation industries. Certainly one of the traditional ones is fossil power, coal, oil, has a lot of challenges for the environment. And we're trying as an industry and as engineers to make that more efficient, more clean, and move away from it to more cleaner sources of power generation. Another common one that you're going to see is natural gas power generation. Then there's combined cycle, biofuels, nuclear fission, traditional nuclear fission power plants. Then there are some other applications of nuclear fission coming on board, including small modular reactors and non-traditional power generation, nuclear power generation. Um, Also, a lot in the news is nuclear fusion and test facilities, geothermal, combined heat and power. So I made a matrix here of different types of applications within these industries over here on the right. And so really, aside from the areas that are grayed out, where just it doesn't not really relevant, our software gets used in all of these areas. Okay, so one is certainly primary cooling and sometimes heating, depending on the type of application that you're in, for example, like combined heat and power. But certainly primary cooling systems, auxiliary systems, which can be backup cooling systems, and all kinds of other auxiliary systems that go along with these facilities. Handling high and low pressure steam, handling natural gas, fire water systems that are fire water specifically to manage the fire suppression systems with these facilities. HVAC systems that are industrial HVAC system for these facilities, and emissions environmental type issues. And so all of these issues down here are places where our software gets used. We have a whole bunch of case studies and technical papers. I think it's like 21 different case studies and technical papers. And so what I filled in are some of the ones that we have available, and I'm going to give you a link at the end of whatever these areas might be relevant to what you work on. Like, for example, in the area of traditional fossil coal and oil type power plants, primary cooling and heating, we have at least one Fathom case study and one least impulse case study or technical paper. And so that's what that means. And then each of these areas, this is one where we have on high and low pressure steam for fossil industry is an Aero and an Extreme case study technical paper. And so each of these places are areas where we actually have a user story of where they've used our software in these particular applications. So it's actually probably almost about 25% of all of our available case studies are around power generation, because we have just been used so heavily in that industry for so long, in those industries, plural. Okay, so moving on from here. So out of all of these, I could have picked from, I said 21. And so since we only have an hour today, and even if we had more time, I think you would get bored if I went through 21 different types of case studies, okay? But I thought it would be of interest if we can dive in, a little bit of a deeper dive into some of these case study applications on some of these systems. So I tried to do a variety of products and a variety of systems, okay? So the first one we're gonna do is a Fathom case study. It's an auxiliary cooling water system in a traditional nuclear fission power plant, okay? The second one we're gonna do is a combined heat and power application that covers both primary cooling and heating and also auxiliary cooling and heating systems. So we're going to talk about another case study on that, and we'll dive in and talk about what that customer did. We're also going to talk about a natural gas, gas turbine supply piping application with AFT Aero, okay? So we'll talk about that, something a customer did there. On Impulse, we're going to talk about a combined cycle power plant where this application was really around the primary cooling water system for the steam turbine side condenser cooling water system in this case right here for Impulse. And then the final one is an AFT Extreme. This is really a technical paper. We are not at a point yet we have had any good applications for case studies on Extreme, so we don't have any published yet from customers, but we have a technical paper that hits high and low pressure steam that hits all fossil coal oil combined cycle and traditional nuclear fission, and really any steam piping, but these are particular high and low pressure steam systems that you would see that where Extreme has some publications that we did, and actually these are ones that I did personally with ASME conferences. So there's 5. So we're going to talk about 5 areas where there's been applications of our software around power generation. Okay. Further, there I didn't give an exhaustive list of all the things that touch on power generation, and there's a whole other area of energy storage. Okay, certainly hydroelectric power, depending on your region, around in North America, certain areas of Europe and other parts around the world. Hydropower can be a big component. Our software has been used on modeling systems with Francis turbines, Pelton turbines, and also pump as turbines, PAT systems. Our software has been used on that. We also get used by OEMs in the power industry, steam turbine manufacturers, gas turbine manufacturers, cooling tower manufacturers have used our software to help simulate their equipment. What goes on inside of these pieces of equipment. And then also for energy storage, I'm aware of our software being used on pumped hydro and also thermal storage. And one of the applications I talk about today is actually going to hit, the combined heat and power application on Fathom has a significant thermal storage component to it. So our software gets used in those areas. It's probably broader what I'm telling you here, but these are ones that I'm kind of personally aware of that our software has been used on by customers. Let's talk now about the first case study that we want to get into, okay? This is a hydraulic model calibration of a nuclear plant service water system, okay? AFT Fathom case study number 1. So the application here was for it's a North American energy utility called Duke Energy. If I'm not mistaken, they're last I checked, they're the second biggest power utility in the United States. This particular power plant is the McGuire Nuclear Station in Huntersville, North Carolina. Okay, over here on the right is just a photo of the Duke McGuire Nuclear Station. I had the privilege about 10 years ago of visiting this power plant. Those of you who are outside the United States and aren't as familiar with where North Carolina is, there's a little star here of where this nuclear power plant is over in the eastern part of the United States. This particular nuclear power plant has 2 units, Unit 1, Unit 2. Unit 1 opened for commercial operation 1981. Unit 2 began in 1984. The project involved both units. And the project goal was to develop and calibrate a hydraulic model of the nuclear service water system, which they called the RN system, of the B train. Okay, the B train supplied cooling water that went into both Unit 1 and Unit 2. These systems were backup cooling systems for Unit 1 and Unit 2 reactors. So those of you in the nuclear industry, these were safety systems. So all of this project was done with the software and the project done within the cores of like ASME and QA1 safety systems, okay? At the time this project was done, it was after the Fukushima accident in Japan. And so the systems had some mandatory modifications they had to go through for improved safety. And so part of the project was modified piping that hadn't been done yet. They wanted to modify the piping, but they wanted a calibrated model to help them understand what would happen when they did the piping modifications, calibrated to measurements, okay, and validated. This is an overview of the system. So the cooling water came from a lake that was adjacent to the power plant called Lake Norman. And then they also had an auxiliary cooling water pond that they could draw from if there was an issue drawing from Lake Norman. The cooling water came in. There were, for the B train, there were a pumping system that came from that we called Unit 1 B train, Unit 2 B train, and then it went in and provided cooling to a whole bunch of heat exchangers on Unit 1 and then on Unit 2. The heat exchangers, there were 3 what we called primary load heat exchangers that took the lion's share of the cooling water. And then there were a bunch of minor load heat exchangers, I don't know, maybe 15 on each side that had lower cooling loads. Okay, and that was both on the Unit 1 and the Unit 2 side. And then there was some cooling water which went out to a auxiliary feed water system as a backup to the main feed water system. The major load heat exchangers, which are the KD, KC, and NS, they are supplied by piping with diameter which was greater than 6 inches or 150 millimeters. Some of it was much larger. And the minor load heat exchangers all had piping less than 6 inches, 150 millimeters. So that's what happened in the piping here. I'll show you some diagrams of that. Each system that came through on each of the B train systems had flow of about 20,000 GPM or 4,500 cubic meters an hour for each of the trains. So what had happened over the years since they were pulling raw water out of this lake is they would open up the pipes, the piping that came in all of the piping that came in the cooling water system itself. And this is what it would look like inside. So there was significant scaling that increased the roughness of the piping, but it also, you can see on the right here, how it literally like decreased the diameter of the piping, okay? Just from the raw water flow. And that was buildup and corrosion of the piping. So what the utility wanted to do, the Duke Energy, is they would go in and treat the piping to clean it out. But where there was the untreated piping that looked like this, they took flow measurements around and I'll get into this, around the cooling water system, and they wanted to calibrate the model to the in situ piping that looked like this, so that they could actually use the model going forward in the future with the piping that looked like this, okay? So what they wanted to do is they wanted to modify the piping internal diameter because of the scaling buildup, okay? And basically shrink the diameters to account for that, and then also change the pipe roughness according to measured pressures and flows. They didn't have pressures and flows for every pipe. They had just a certain number, about 20 around this each of these different trains of operation. Data sets were provided from different operational configurations. So it wasn't just one measurement. They would measure with different things in and out of service. So they were trying to calibrate not just to one set of measurements, but to different set of measurements on each pipe system. So it was like different flow measurements, but the same scaling and pipe roughness, okay? There were 15 to 20 flow and pressure measurements taken in each data set that needed to be matched. And previously, Duke Energy had done this manually, tried to do this manually. And you can kind of imagine trying to do goal seeking manually when you've got 15 to 20 variables that you're trying to match. And so it's a tedious process and not that accurate. So this is really a good application for the AFT Fathom GSC module, which is well suited for multivariable goal seeking, such as this project. Far as I'm aware, AFT Fathom and the GSC module is the only software in the that exists in the market, excuse me, that can actually do this kind of a project, automated multivariable goal seeking to try to match the scaling and the pipe roughness versus met flow and pressure measurements. And so this was done at the time back around 2013, 2014. This is a model of the 2B RN system. So just kind of real quick here, this was the supply from Lake Norben, and this is in this Fathom model. And then if there was a disruption in cooling water supply, there was a backup pond that could supply. These were the two cooling water pumps that drew in. This one came in for the 2B, this Unit 2B train that flew in. That's what we're seeing here. There's a whole other set of piping here for the unit. Oh, this would be the other one for the A train for Unit 2, and this was A and B train for Unit 1. So there was a whole other model developed for one of these right here for the 1B system for the B train on Unit 1. Okay, the flow came in through the pump and it had it to provide cooling water to all of these heat exchangers. The red ones here, what we call the major load heat exchangers. And so those ones are the most important and the most flows. And then there were a bunch of minor load heat exchangers you can see down here where cooling water had to also be supplied. So the whole goal here was there were 3 different measurements for this system. And we were trying to take the piping in here and vary the pipe roughness and scaling to match measurements, the 3 measurement sets for this system, okay? Satisfactory calibration was achieved except in 3 minor load paths which were a bit difficult, and there was not very good data. On the 1B system, Unit 1B train, there was partial calibration because they didn't have sufficient measurements all the way around the system. So there was flow data for all the heat exchangers, every single heat exchanger. There was pressure data only for the major load heat exchangers and not for the minor load heat exchangers. So there was less data to the calibration here. On the Unit 2B train, we had flow and pressure for all of the heat exchangers in that whole system, okay? Using the automated goal seeking, we were able to match their flow measurements within 2.1% and all the pressure measurements on average on the 1B system within 1.2 psi. And on the 2B system, the flow is measured within 2.3% on average and 1.4 psi. So that was the end result on that particular project. So in the end, they had a model of, they had two models, the 1B and the 2B system that had been calibrated for their in-operation piping, so they could use that for design decisions going forward with, for example, changing pipe routing. Okay, second case study here. This was a more recent case study. This came in, I think, last year. Very interesting. It was a state-of-the-art combined heat and power plant. This particular project was done by a company called Enka in Hamburg, Germany. So those of you who are maybe not as familiar with your geography in Germany and Europe, this particular facility where Hamburg is right here in Germany, northern part of Germany. The problem that was encountered here was that they had a new system at the, and you have to excuse, probably not going to pronounce the German word here, Drahtenau combined heat and power plant, and they wanted to do combined heating and cooling, and it was very involved. I'll get into this a little bit. There were 9 heat sources, including waste heat from adjacent industrial processes and a natural gas power plant. The tool they used was Fathom. They used Scenario Manager extensively to model the different configurations for winter and summer and different on-load, off-load cases. And they talked down here about some of the cases that they got into. What they were able to do is on this new design is validate line sizing choices. They sized pumps, control valves, and heat exchangers, and they used the scenarios to analyze a range of operating conditions with various waste heat and heat demands. Okay, some of the interesting things on this, and I'll show you a picture of it in a moment. This was, maybe this is common in Europe, I don't know, but this was amazing, the types of things that, that this application got into. So first they had a combined cycle power generation. They had gas turbines and steam turbines. So this system of cooling and heating water that they used to transfer in and provide heating and cooling for these different users was they provided heat, a preheat for gas turbines. They also provided cooling for the steam turbine condenser, and they had various other auxiliary heating and cooling needs for the power generation part of this facility. They also had local industrial waste heat intake, or they had to supply heat too. So they had waste heat coming in from an adjacent steel production facility and a sewage plant, and then there was also an incinerator nearby, and so they supplied heat. Transferred heat to this incinerator. Also in the winter, they had a thermal energy storage tank storage, or multiple tanks is what I'm guessing. That was 50,000 cubic meters in size, or 13 million gallons of hot water that could be used to disperse heat as needed 24/7 in the winter. The heat transfer, they also used heat transfer modeling in our software, and I mentioned that earlier on, is that a lot of pipe flow modeling, they can't actually do heat transfer and the thermal balance on their system. Fathom can. I've been doing that for almost 30 years, and they've made extensive use of that with heat transfer in the pipes and the heat exchangers, 17 heat exchangers, where they had heat going in and out and did a complete thermal balance on the system. Extensive use of Scenario Manager to manage 17 operating scenarios. So those are some of them that were listed here. Okay. This is the model. It had nearly about, 250 or so pipes in the model, 250 pipes, 250 junctions, okay, that they developed. The blue that you can see on here was the cold water piping, and the red was the hot water piping. And we'll drill into a little bit more of the detail. The thermal storage was right here in this reservoir right here. These were the main pumps that drew out from the thermal storage and stored actually, I take this back. It wasn't cooling water. It was cooling water. Okay, and then they could distribute out through the system. Okay, and then there were additional heat exchangers in here and some auxiliary pumps that pop up down here for driving out into this other portion of this whole major facility. Okay, let's talk. So this over here on the left, we're going to talk about the management like of the captured waste heat. Okay, so this was the image we just showed, and we're going to focus in on this part right here. This was the heat extraction portion of the plant where waste heat from industrial suppliers and from the steam's power cycle are captured through these heat exchangers in here. And so that was this part of the model coming distributing in here. And then this lower part out here, they actually took the heat that came from these different sources, and they provided this heat to different users, and one of them was literally a district heating supply to the residential people who lived around this facility in Hamburg. And so this happened in this part of the system down here, where there was distribution to a district heating system that took place for local residents. That was part of this entire integrated system. So this was quite an amazing integrated system between industry, residential, power generation, that all have different heating and cooling needs. Okay, we're going to move on to case study number 3 now. This is an AFT Aero case study. This is done by a company named Fern on the gas turbine analysis. Okay, they had some modeling challenges. One is they had to model sonic choking in multiple parallel paths on the feed to this gas turbine, and they also had to accurately model that sonic choking. And then also, what was really the bottom line is they had to accurately model the flow and temperature distribution at multiple fuel discharge points. Okay, so the company that worked on this, Fern Engineering, they are located in the Northeast United States, Massachusetts, outside Boston. So again, if you don't know your U.S. geography, it's up in the northeast of the country where they did this project. That's where the engineering firm is. I don't know where the installation was. They didn't tell us where the installation of this gas turbine was. Okay. Their problem is there's an issue that happens with fuel supply to turbines called exhaust gas temperature spread, EGT spread. Okay. And if you don't have even distribution of flow and temperature, you can impact the reliability and the lifespan of operation of the gas turbine. Okay. And just basically caused by not having even distributions of flow and temperature. So they wanted to understand on their supply piping to the gas turbine, what was the EGT spread, okay? So they developed a model on AFT Aero, I'll show you in a moment, that's had all the supply systems, fittings, length, supply, proximity, determine fuel supply variation. And they also benchmarked the model for sonic choking for test data, and I'll talk about that as well. So the solution was a model that estimated flow and temperature variation due to expected tolerance variation, which then informed them on their EGT spread, which would then feed into their analysis for reliability on the turbine. The turbine, okie doke. Let me get back on here. The turbine was a Rolls-Royce Avon gas turbine. This is now owned, the production on this gas turbine is now owned by Siemens, originally developed for aerospace applications. I don't believe it's used in aerospace anymore, and it's used just for power generation today. All right. To get my advancer here. Okay, so this is the AFT Aero model that they developed. This was the fuel supply over here on the right, and then the fuel went out, and then all of these 8 different fuel nozzles would really go around the periphery of the gas turbine, okay? And then these were the 8 represented 8 fuel injection points, okay? One of the challenges here is that there was these orifices that existed before the fuel nozzles, and all these orifices experience sonic choking. So in order to get an adequate measure or prediction of what's going on with the exhaust gas temperature spread, we had to be able to predict what was happening thermally in all of these different systems and the flow distribution going around, and then what happens in the sonic choking, and do that accurately, and then what happened across the sonic choking point downstream of these sonically choked orifices, so that we could get a correct and accurate temperature delivery at each one of these points and flow, okay? So so the company, when they were developing this model, they said, well, you know, how accurate can AFT Aero actually simulate flow through an orifice? So they actually built a test rig down here that looked like this. And it was flow that came from a low pressure air supply through a flow meter. They had the choked orifice down here. And they measured flow and pressure in this system. And this was the data that they measured, and these were the Aero calculation results. So you can see flow rate down here in pounds a second and kilograms a second. And Aero was correct within like on flow, much better than 1% on the flow rate going through the system. And then pressure within 0.3 PSI, 0.03 bars, okay? So they went ahead and did this. They told us what the results were. And then this convinced them that Aero was doing a good job of predicting pressure and flow through choked flow points. And then they went ahead and trusted Aero to do the bigger system over here on the left. Okay, let's go ahead and do case study number 4. This was a cooling water system at a combined cycle power plant. And this is an impulse case study, okay? This was done by an engineering contractor in the United States called Kiewit Power Engineers. They're in Kansas. The facility, I'll show you in a moment where the facility is. But the engineering was done in Kansas. The problem that they had was the circulating water system. They needed to evaluate what happened with pump trip and pump startup scenarios. What happened from a water hammer transient point of view, okay? Safe shutdown, safe startup operations, pressure extremes, and protecting especially the high expensive equipment, or which were the condensers, okay? They'd ensure catastrophic events were avoided, equipment could handle normal and small transients, okay? First, what they did is they had an AFT Fathom model that existed of this cooling water system, a typical, you know, Fathom model. And then they imported that rather than build from scratch, and they were able to start their impulse model from a Fathom model, which saved them a lot of time and effort. The model was color-coded to improve readability. The model had 46 scenarios for pump trips and pump startups, and it's all in a single model file. They generated all kinds of graphs to understand what was going on, okay? I'll show you what the model looked like in a minute, but the facility is in New Jersey. It's called the Woodbridge Energy Center. It's in New Jersey, right across the river from New York, from Staten Island and New York City. Up in the upper northeast part of the United States, the Woodbridge Energy Center. It's a 725 megawatt combined cycle power plant, opened in 2016. They used I already mentioned Fathom, but we're not going to talk about that. We're talking about the impulse part here. A water hammer and a primary cooling water system, a very common application for AFT impulse, is to understand what happens when your pump trips and pump starts, okay? There were 2 vertical turbine pumps providing total flow of 158,000 GPM, 36,000 cubic meters an hour total flow. They had pump trips modeled, pump startups modeled, and all kinds of scenarios with variations of those. They had cooling that was done by 14 cooling towers. You can see the cooling towers over here on the right. There are 14 of them. And as I mentioned already, they imported all of this from a Fathom model, okay? So this is the model that they developed in Impulse. The color coding in here was not hot and cold, okay? So certainly one of the important parts of the analysis was to make sure that pressure was handled safely around the 2 condensers that they had, okay? So they had condensers with vacuum air valve protection, typical around the low pressure condensers. And they also had a auxiliary cooling for a component cooling water heat exchanger in here. So they are providing cooling to each of these three different paths. Okay, the green color they put in there was like the cooling part of the system. Okay, the red color for them meant that the piping was underground, and then the blue was piping that was above ground piping. Okay, the pumps, the two pumps that provided the 158,000 GPM of flow, vertical turbine pumps, were over here on the left, and those were anybody in here, any fans of Flowserve? They were Flowserve pumps. And then the cooling towers were all down here, cooling tower discharges down here. And then this is a 99% closed loop system because the cooling tower cooled water would then feed back into the basins and then feed these pumps again. Okay. This is a screenshot of the scenarios. I think there was 47 scenarios that were done by this engineer, looking at two pump start, a two pump trip, and then a single pump trip, one pump running one trip, etc. Different types of possibilities for managing the air for low pressure protection right here around the pump discharge and also around the condensers. Okay, so this is a very common. I've seen this many times, hundreds of times. People using impulse on systems like this, a very common thing. Nothing terribly unique about it, other than it's something that's AFT can do, and not everybody can do with our impulse software. That a lot of other companies just don't get into that, and we do. So, and we can take your Fathom model just like this and bring it in and kind of start up for the cooling and the water hammer prediction. Okay, so I wanted to show you some applications around AFT Extreme. So myself, I guess and some other AFT engineers is we have been presenting some papers about Extreme in some of the ASME conferences and in recent years. And so I'm going to talk about some of the things that came out of this. Particularly focusing on a couple papers that I presented at an ASME conference, PVP conference in 2022. Okay, predicting transient pipe forces in power plant steam piping is what the papers are really about. Common practice methods for estimating piping loads due to steam hammer have been used since the 1980s. Some recent studies that came out starting about 10 years or so ago by other companies were indicating that these methods were not conservative. They were not able to really explain why, but they were calling into question some of these methods that have been used. And these are methods used on forces in steam piping that are used to assess what type of pipe supports are. And these methods have been used, you can look in the literature, have been used in design of a lot of nuclear power plants, have been used with these methods. And the important finding that some of these studies were indicating that they were not conservative, that the forces and the associated requirements on support piping were not being designed in a conservative manner, which is always scary for an engineer. So when AFT Extreme, we were getting this online about 5 years ago, came out commercially available about 4 years ago, but we had it really in an advanced stage, and we started looking at some of these studies, and I was looking at doing this personally, actually, and we were able to confirm that these studies were, in fact, because there was some questioning whether these studies were valid, and we were able to confirm that they were, in fact, valid, and we were able to provide the detailed analysis to explain why these methods since the 1980s were not conservative. What was missing in these analysis? We were able to, AFT Extreme was able to help us understand why, and we presented that at this ASME conference. So we'll talk about this here a little bit. Why are transient forces important? So if you're purely a fluids person, then this is something you don't have to worry about. That's usually something that comes about in your mechanical group, where somebody has to provide the pipe supports. especially, if it's piping that's above ground piping, that we have pipe supports that are going to be able to safely be able to support the piping to handle these forces, okay? So why are they important? Well, fluid transients like water hammer, surge, steam hammer, etc., they cause transient forces in the piping. These transient forces can be very large. 10,000 pounds, I'm going to show you an example today, the one that's going to be 50,000 pounds, which is like 50 kilonewtons, maybe up to over 200 kilonewtons. Those are common in some of the, especially larger diameter piping, okay? The resulting stresses can cause sudden or fatigue failure on the supports, especially if the supports are not strong enough to handle the loads. Designing a safe system requires accurate transient fluid forces that can be put into your pipe stress analysis, okay? So where do you get those accurate forces from, okay? Well, I'm not going to talk about this in detail just because it's if you're interested in this, you can go read some of the papers that we have, and we've done webinars on this before. I've done it in conjunction with some of our other staff, okay? But just in a real nutshell, what happens in piping across elbow pairs, we're going to focus right here, what happens between points 1 and 2, elbow 1, elbow 2, and the piping in between, okay? And if that piping is not supported, then any loads that happen have to be taken up by their other piping, and the piping will move. And we'll look at that, what that might look like. Normally, you don't want that to happen, so you have to have pipe supports that provide some rigid supports in this particular run of piping. Same thing is going to happen in the vertical runs, but right now we're just going to focus on this horizontal run. We'll call leg 1, 2. Okay, and so when there's a steady state velocity going through, then then there is balance in the system. All the forces add up to 0, and so there's no movement on the piping. There's no transients causing movement. Now, what happens if you get a transient, for example, a quick closure of a valve? Excuse me. You get high pressure on the right, which is going to move in a wave down the piping. And when that wave is between these two elbows, you'll get a force. And this is a force versus time over here on the left, okay? And you'll get a force. And the question is, what's the magnitude of that force? And also, what's the duration? And then also, some things get into reflections and things like that, okay? So that's the question, is what does that force really look like, okay? So we created this animation that gives you an idea of what kind of happens in a pipe run, okay? So we're gonna say there's this flow, it's low pressure, going in through this valve and just discharging out through a valve. This is not with steam, this is with water, but a similar thing happens in steam and with gases, okay? Is that when you close this valve, it generates high pressure, and when that pressure goes through, it has an imbalance that happens on the piping, and it causes the piping to move, okay? You can see this on YouTube in different videos. So trying to predict the loads of what's happening, that is the question here that we want to kind of get into, okay? So in order to figure out what's happening, all of the fundamental parameters of pressure and flow, they all come out of a simulation with like AFT impulse for liquid transients and AFT extreme for steam and gas transients, okay? And the fundamental principles are conservation of mass momentum. And so we have all of the building blocks in the piping, for example, of all these different forces that add up according to Newton. So, and this is basically Newton's second law, which is the sum of all the forces equals ma. And this is what the integral looks like if you're trying to do a force balance around a system like this, okay? What you see, unfortunately, is what a lot of engineers have done traditionally, just because of a lack of data and time, is they've only paid attention to this pressure force at this end and the pressure force at this end, and they've neglected everything else. And we've shown in some of our papers and other webinars that you can miss. The other things can be super important, and you can miss things if you don't do this properly. So this is what the math looks like. If you're curious about applying this math, we have some technical papers we published in ASME that I helped co-author that talk about pulling out this data out of the impulse and AFT extreme results and adding up the pieces properly to tell you what the forces are on something like this, okay? So if we go forward, this is an example that came from a publication in 2015, 10 years ago, from a couple gentlemen that I actually had a chance to meet, Ben Ravanati and John Gray. They worked for Sargent and Lundy in Chicago, and they presented this case study on a flow that was 1,000 psi, about 7,000 kilopascals steam supply going through piping to a turbine supply. There's a turbine stop valve that closes, and when it does, it generates loads in the intermediate piping. And the thing we're going to pay attention to are these green stretches of piping. The different legs, run lengths in here, you can see in feet and in meters. The total length of all the piping was about 2,000 feet or 600 meters of piping diameter, was a nominal 30-inch piping, 29-inch ID, 0.74 meters, pressure supply, temperature supply, flow rates, etc. Turbine stop valve closes in 1/10 of a second to protect the turbine, okay? So they went ahead and did a study on this, and we dove in, and they said that there's bad news on the conventional methods, and using Extreme, we said it's bad, it's even worse than Ravanati and Gray. We confirmed what Ravanati and Gray reported in 2015, and we were also able to take a deeper dive and explain why this is happening, okay? So the traditional predictions of the forces, and this is leg 1, 4, 7, 10, all the way out. They're the green legs. So leg 1 is right here. Here's 4, 7. So as you get farther and farther away from the stopping valve, these are the forces that happen over time. And so you could see that the traditional method was this method by an engineer named Goodling, who worked for, which is today, it's now I think Worley Parsons in Pennsylvania. And so you could see on the very first leg 1, Goodling's method was pretty darn accurate according to the Extreme results. So the red one was the method that was commonly used in industry, and the other colored ones are the ones that are predicted by Extreme. And then you could see as you get down different legs for the way the forces get higher and higher, okay? And so you can see like on this farthest away leg, we've got forces that are 300%, 200% higher than what Goodling predicted. He said about 15,000 pounds over here is newtons, and you can see it's about 65 kilonewtons. And it was actually 3 times as large farther away. So that was big news, okay? So if you're interested in that further, again, we have some webinars around that. You can look at our library, and we have some technical papers that were presented at ASME conferences. I and some other folks at AFT have put together. Okay, drawing to some conclusions here. AFT software has been heavily used in the power industry for over 30 years. So power industry, I told you, like all of our case studies and technical papers, about 25% of them are around power generation. It's a big area for us. You work in these industries, you probably know our software. If you don't, haven't used our software, so we are heavily used and proven in these industries, okay? Many of the world's largest power generation organizations, they rely on AFT software for doing their daily engineering work, both engineering design firms and also utilities, power utilities like Duke Energy, I talked about earlier. AFT's family of software products offer the broadest range of products for power generation than really anybody out there in the marketplace. We have 4 products with numerous add-on modules, such as like goal-seeking module we used for the that got used on the Duke Energy project, that let you do the broadest range of fluid system type analysis of really anybody in the marketplace. Many powerful capabilities were unique, and you only have an AFT software. There's certain things you want to do. We're the only ones who really do it. AFT has over 20 case studies and technical papers for power generation applications, which show the amazing breadth of AFT software in these industries, okay? I'm not going to go over these, but there was I'm going to just show you that this is a list with a hyperlink to all the different case studies and technical papers that we have around power generation. I think there's 21 of them, and there's a document, a PDF document provided with hyperlinks. So you can find all these on the AFT website, but if you want something consolidated for the power industry, here's a list. The first page is fossil, coal oil. There's a fossil natural gas. There's one here that we have in a combined cycle plant. And then we also have a number of applications around traditional nuclear fission. We have actually a couple of case studies around nuclear fusion, some of the test facilities done to try to develop nuclear fusion power. We've got two case studies around that. We have two around combined heat and power, okay? And so you can find those links in that document attached to this webinar if you want to go research those further. And I've got 5 minutes left. And so I don't see any questions that are put into the chat. So if you have any, wait a sec, I'm looking in chat and I'm not seeing anything in chat. I'm not seeing anything in questions either. So, so let me see if David, one of our people here, I haven't seen anything else around this. So now's the time if you have a question. And we got 5 minutes left. All right, I am not seeing, and unless you guys are typing too slowly, I'm not seeing any questions coming in. So with that, I think we've come up, just give you about 5 minutes back by concluding a little bit early. Thanks for your attendance today. If you do have any questions, if you think of anything, or you go out and look at some of the studies I've done and you think of anything, be sure you can email me or email anybody here just through general AFT through our website. We'll be glad to try to help you answer your questions and see about any applications that you might have that you're interested in applying it to. We can help you answer those questions. So with that, I'll call it conclusion, and there will be a recording done if you need to go back and look at any of this over again. Otherwise, I appreciate your attendance today. Have a good rest of your day.